Welcome. This presentation provides a deep dive into the Hadoop NodeManager, the crucial slave daemon within the Yarn architecture. We will explore its role in HDFS and resource management, providing a comprehensive understanding of its functions and importance. Presentation date September 3rd, 2025. Let's begin with the fundamentals. The NodeManager, often abbreviated as NM, is a per-node slave agent in the Hadoop Yarn architecture. It is not a transient process, rather, it is a Java daemon that runs continuously on every slave machine within the cluster. The key insight here is that the NodeManager is the foundational component that enables Hadoop's massive scalability. It does this by distributing the responsibility of resource management across every single node, rather than centralizing it, which would become a bottleneck. The NodeManager has several core duties. First, it manages containers and actively monitors resource consumption, such as CPU and memory, on its individual node. Second, it works in constant coordination with a master resource manager for centralized cluster-wide management. And third, it is responsible for ensuring efficient resource utilization and performing critical node health monitoring to maintain cluster stability. Now, let's visualize where the NodeManager fits. This diagram illustrates the Yarn master-slave architecture. At the top, we have the resource manager, or RM, acting as the master. Below it, we see multiple slave nodes. On each of these slave nodes, two key daemons run side by side, the NodeManager itself and a data node daemon for HDFS storage. The arrows represent the continuous communication. The NodeManager sends heartbeat signals and status reports up to the resource manager, keeping it informed of the node's availability and health. The first key function is container management. The NodeManager is responsible for creating the abstract containers in which application tasks, like map or reduce tasks, actually execute. It meticulously monitors each container's resource usage, including CPU and memory, against its allocated limits. If a container exceeds its limits or if instructed by the resource manager, the NodeManager will terminate it to protect the node's overall health. Function 2 is health monitoring. The NodeManager acts as the onboard doctor for its node. It performs regular health checks, primarily on the disks. It also has the capability to run custom scripts configured by an administrator for more specific health checks. The status from these checks is then reported back to the resource manager, which uses this information for scheduling decisions. Third, resource management. The NodeManager is the local resource tracker. It knows exactly how much CPU and memory is available on its node. It also manages designated disk directories for temporary files and container logs. This local management is vital for the resource manager to have an accurate, aggregated view of total cluster resources. Lastly, the NodeManager manages auxiliary services. These are supplementary services that support specific frameworks. The most common example is the shuffle handler, which is essential for map-reduce jobs to efficiently transfer and sort data between the map and reduce phases. Let's follow the lifecycle of a container managed by the NodeManager. The process begins when the NodeManager receives a request to launch a container from the application master. Step 1. It localizes the resources needed by the container, such as JAR files and dependencies, from HDFS to the local disk. Step 2. It launches the container process. Step 3. It continuously monitors the container's execution. Step 4. Once the container completes, the NodeManager cleans up the localized resources. Finally, it reports the container status back to the resource manager. Diving deeper into disk health monitoring. The built-in disk health checker verifies two critical things: that it has the correct permissions to write to the disks and that there is sufficient free space. It checks the configured local directories and log directories. These checks run at configurable intervals with a default of every 2 minutes. If a disk fails these checks, it is marked as unhealthy. For health checks beyond disks, the NodeManager can execute external scripts. Administrators can write custom scripts to check for any node-specific condition, like the status of a specific service. If the script outputs the word error, the NodeManager interprets this as a health issue. The timeout for these scripts and their interval of execution are both configurable. So, how is the overall node health determined? A node is marked unhealthy if multiple of its disks fail the health check, or if any config of external health script reports an error. This status is a red flag for the resource manager, which will immediately stop assigning any new containers to this node, preventing further tasks from failing on a problematic machine. Here are some of the most critical configuration parameters for health monitoring. For example, yarn.NodeManager.diskHealthChecker.enable defaults to true, and yarn.NodeManager.diskHealthChecker.max disk utilization per disk percentage sets the threshold for disk space usage, defaulting to 90%. Exceeding this threshold will mark the disk unhealthy. For resource management, the NodeManager uses two key types of directories. The local dias are for temporary files during application execution. The log dias store the standard output and error logs for all containers. To enforce resource limits, the NodeManager uses Linux control groups, or C groups, which ensure that a container cannot exceed its allocated amount of CPU and memory, providing strict isolation. To ensure fault tolerance, the NodeManager can be configured for recovery. By setting yarn.NodeManager.recovery.enabled to true, the NodeManager will persist its state. In the event of a restart, it can recover its previous state and even reconnect to running containers, minimizing application disruption. A key requirement for this is to configure the NodeManager's RPC server to use non-ephemeral or fixed ports. The co-location of the NodeManager with the HDFS data node is a masterstroke of Hadoop's design for performance. It enables data locality, allowing computation to be scheduled on the same node where the data resides, drastically reducing network traffic. Furthermore, it enables short-circuit reads, which allow a container to read local data directly from disk, bypassing the network stack entirely. For instance, a 400 megabyte file can be read in parallel by multiple local containers extremely efficiently. Following best practices in configuration is essential. For memory, correctly set yarn.NodeManager.resource.memory MB to the total physical RAM available for containers, and configure the vmem/pmem ratio to control virtual memory usage. For CPU, accurately set the number of virtual cores using yarn.NodeManager.resource.CPU vcores. For health, prudently set disk utilization thresholds and implement custom scripts for any critical node services. Operational vigilance is key. Monitor key metrics, the number of active node managers, unhealthy nodes, resource utilization, and container launch success rates. When troubleshooting, start by examining the NodeManager logs, then check disk health, network connectivity, and configuration files. For security, ensure auxiliary services are properly isolated and that Kerberos authentication is enforced to secure communication within the cluster. In conclusion, the NodeManager is a critical pillar for cluster operations, fine-grained resource management, and overall fault tolerance. It is the daemon that enables Hadoop's renowned scalability and flexibility. Looking ahead, the role of the NodeManager continues to evolve with support for node labels for heterogeneous clusters, GPU scheduling for AI workloads, and Docker containerization for improved application packaging and isolation.